fun to mess around with.
I see. All right. Well, another exciting day of circuits ahead of us, so we can have some fun. There we go. Just in the way of announcements, again, our exam is Thursday night from 6 until 7:30. It's in IRC 214. I'll try to get there a little early so you have a little extra time or whatever. But as far as the exam, I have all of the circuits designed that I want to test you guys on, and I just don't have numbers, and I haven't pulled together all of the details of what the questions look like and written it out. So I've got all the circuits ready to go. Should be able to get it done before lunch today. So what that means for on-campus students is not much. What it means for online students is that you should be able to see the file available for downloading and getting ready to do your thing with pretty soon. And I will definitely write up some instructions on how I expect everything to go for that online stuff. But quizzes, I took them back to my office and set them down on the desk, and I will grade them later today. As much as anything, the online students just could have finished their exam, or their quiz. So I didn't feel like I'd like to grade them all at once instead of in two batches. But are there any questions on anything? Okay, so we started talking about these Thevenin and Norton equivalents yesterday after doing another example of superposition. And just to, again, give you an idea of what we're trying to do here, before we had PSpice and before we had calculators that could solve many simultaneous equations, we had guys named Thevenin and Norton and Meyer who were all working on ways to make our circuits look simpler and to get them down to where we just have essentially two resistors and a source, where one of the resistors was our load, what we were interested in, and then the source and the other resistor characterized everything else that was happening in the circuit. Thevenin gives us a series voltage source and resistor, and in Norton we get a parallel current source and resistor. And so to some extent, if you're studying, or if you're trying to solve for a current, maybe it would be a little easier to deal with a Norton equivalent and do a current divider. If you're solving for a voltage, well, maybe it would be a little bit easier to do a Thevenin equivalent and do a voltage divider. But both of them aim at the same thing. Make it easy to characterize a certain parameter of the circuit and kind of see what happens as that parameter changes. If you increase the resistance, decrease it, or whatever. And so we came up with this way of trying to describe exactly where the equivalents came from. Essentially what it boils down to is that linearity and superposition allow us to say, we can characterize the voltage across two terminals and say, well, if I know what that voltage is, then I can replace that other side of the circuit with a voltage source. And there's going to also be some short circuit current that, again, if I were to kind of yank out that load and then put a shunt in to short circuit it, there would be some current running through there as well. And the relationship between those two currents, so you've got the open circuit voltage and the short circuit current, the ratio between those gives you the Thevenin resistance, or the equivalent resistance seen looking in when all of the sources have been turned off in the appropriate way. And so that gives us these Thevenin equivalents. And again, the most important of all of the equations to kind of remember is this one, where VOC, the open circuit voltage, is given as the short circuit current times the Thevenin resistance. And that gives us a way of, once you have one of the equivalents, you can always switch over to the other equivalent pretty quickly. The only question is, how do you get these open circuit voltages, short circuit currents, and Thevenin resistances. And we came up and we started doing some examples, first simple ones and then some slightly more complex ones. So one of the last problem that we did, I guess it would have been Monday, was I guess yesterday, whatever that was where we did the multiple Thevenin equivalents going across the circuit. And it seemed a little convoluted, but I wanted to show you that you can do it as in one step. You can create the Thevenin equivalents in one step. What you do have to do, though, is you have to do a mesh or a nodal analysis of some kind to figure out what's going on. So let me just show you what that would look like. Our circuit that we were analyzing before looked like this. We had a voltage source and resistor and another resistor. Current source and 4K resistor. And then there's a load resistance that was hooked up at those two terminals. But for the purposes of our evaluation here or analysis, it doesn't matter what that happened to be. And so what we're trying to solve for is this open circuit voltage across, which is, while it's technically across both the 4K resistor and the 2 milliamp source, there's no current running through the 4K source. Ohm's law says if there's no current, there's no voltage. So essentially, the open circuit voltage is going to be whatever the voltage is across this 2 milliamp source. Okay, so what is the voltage across the 2 milliamp source? Well, we could write at least one equation that goes around and says, all right, well, negative 12 plus the voltage across the 3K resistor plus the voltage across the 2K resistor plus, let's just call it the open circuit voltage, equals 0. That's just a KVL equation around the outside loop. Well, what do we know? Which of these can we solve for? Do we have enough knowledge? Well, we know that, at least in terms of, we know that what the voltage is across the 2K resistor because we know that there has to be the 2 milliamps of current flowing through it. But we have to be careful that we just defined when we wrote our KVL equation about the current was running, well, that the positive terminal of the voltage was over on the left-hand side, but the current's flowing in through the right-hand side. And so the voltage across the 2K resistor is the 2 kiloohms of resistance times a negative 2 milliamps because it's flowing in the opposite direction than we had defined the polarity of our voltage flowing in. So that's important, or else you won't get the right number. But what is the voltage across the 3K resistor? Well, the voltage across the 3K resistor is the 3 kiloohms of resistance times some current, but we don't know what that current is. And we'd have to do a mesh analysis to solve for it. So let's go ahead and do that. So that's current I1. This is current I2. We already know that current I2 just equals negative 2 milliamps because it is going the opposite direction as the current source is. Write our second equation, negative 12 plus 3K times I1 plus 6K, I1 minus I2 equals 0. Simplify that so you get 9K I1 minus 6K I2 equals 12. Now, kind of the confusing part, or the odd part about this particular problem, is that we say, well, I know what I2 is. That's negative 2 milliamps. So I plug that in here. This should be 6K. So negative 6K times negative 2 milliamps gives us positive 12. We subtract 12 from both sides. And so we get 9K I1 equals 0. And I1 equals 0. Again, I wish that I could give you more insight as to why exactly it could be that we've got this 2 milliamp source that's doing its thing, we've got this voltage source that's sitting there, it's doing its thing, and absolutely no current is flowing through this 3K resistor. I wish I could tell you, but I can't. Suffice it to say, the math works out that there is no current flowing in the left-hand pane of that circuit. And so we say, well, there's 0 milliamps there, so therefore the voltage across the 3K resistor is 0. So let's solve all of this appropriately. And what we should get is that we had, we can take these two numbers. We got, this is negative 4 volts across the 2K resistor. Plug this and this back into that equation, so we get, bring it down here where we've got some room. We've got negative 12 plus 0 minus 4 plus VOC equals 0. Solve, and we say VOC equals 16 volts. That happens to be exactly what we got the first time when we did it in 2 steps. Then we can do the Thevenin equivalent resistance in one big step too. Short out the voltage source. We've got the 3K resistor, the 6K resistor, the 2K resistor, open circuit that current source, and then we've got the 4K resistor. And that's a pretty simple network still to find a Thevenin equivalent, or an equivalent resistance for. We have 3K here, 6K, 2K, 4K. To save you the suspense, the 3 and the 6 in parallel gives us 2, and so then we've got 4, 2, and 2 in series, and that gives us a total of 8. So our Thevenin equivalent resistance still equals 8 kiloohms. So if you were to look back at the work that we did yesterday, you'd find that we had the exact same thing. We had an open circuit voltage of 16 volts. We had a Thevenin equivalent resistance of 8 kiloohms, and we can hook up the load and whatnot. Which one makes more sense to you? I don't know. It's kind of up to you which one you like better. Would you rather do a mesh or a nodal analysis to figure out what that open circuit voltage is for a larger network, or would you rather do multiple simple voltage divisions, which was the kind of the nice part about the doing it in multiple stages, was you didn't do anything more complex than a voltage division or a current division. So whichever one kind of floats your boat. I don't really care which way you want to do it. I would assume one way or the other is going to make more sense, but so that's how you can do it. We said on the slide that if things get nasty, we can do it multiple times, but again, the only point of trying to do it multiple times is to say we don't want to do a nodal or mesh analysis to solve for our open circuit voltage or a short circuit current, so let's not. Let's just do voltage division or do current division, something simple, in order to do our analysis. So let's do at least one more example, maybe two, because this is going to be the only aspect of this chapter that's going to be on the exam tomorrow. Is just going to be this simple Thevenin analysis, and all I'm going to ask you to do in particular is to just develop the equivalent itself. You don't actually have to do any kind of solution. I just want you to show me that you can solve for an open circuit voltage and find a Thevenin equivalent resistance. So, all right, at least one more example, and if you guys want, I will do yet another example with some random problem out of the textbook. Got 6K resistor up here and a 6 volt source. Got a 3 kilo ohm resistor here and a negative 12. It's a 12 volt source, but the polarity is a little weird. Got a 2K resistor hanging off the side here, and then our load resistance is a 4K resistor here, and what we want to do is we want to find out what the voltage is across that. And this seems like realistically it wouldn't be too bad in terms of a mesh analysis problem. There's no current sources to get in the way or anything, but as a nodal analysis problem, you would have at least one supernode, right? Because somewhere, either here or here, you're going to end up, depending on where you put the reference node. But so one of the things that makes this problem at least a little easy is to note that everything to the left, on the left side of the circuit, is already a Thevenin equivalent. We've got a voltage source with a series resistor. And so in theory, one of the things that can tell you is that you don't need to do multiple steps to make this one work. All you have to do is kind of say, well, now I can just go ahead and break the network just to the right of my load, find the Thevenin equivalent for all of that, and kind of go to town with it. Yeah, so that's it's kind of the takeaway of that part. So let's go ahead and break it to the, my notes say to break it to the right, to the left of the 4K, yeah, I want to break it just to the right of the 4K resistor, the load resistance, and start kind of quantifying what's going on. So we've still got most of the same circuit, plus 2K resistor hanging off here, and we want to solve for the open circuit voltage. 12 volt source, 3K resistor, 6K resistor, 6 volt source. Now again, there's no current flowing through this 2K resistor, so it won't contribute anything. And the open circuit voltage is going to essentially equal, to make sure that we get this right, it's going to be the 3K resistance times whatever the current is that's running around this loop, and just go ahead and call it just I, minus the 12 volts because that's the direction that we hit this. So I mean, regardless of how you kind of try to write this KVL equation, and we run into so let's just to make sure that you're clear on this, because this is one of the things that's the most confusing for me. Let's say that we hit the positive terminal of the 12 volt source first. So we hit 12. Because we've defined the current running around that way, it's going to be minus 3K times I plus VOC equals 0. And that gets us to the same position that we had here. You can do it going around the other way. So we say, well, we hit the 3K resistor first, so 3K times I minus 12 minus VOC equals 0. But all three of them are equivalent statements of the same thing, that whatever the open circuit voltage is going to be the voltage across that 3K resistor minus 12. So what we need to do is we need to find that current. And that's a pretty simple KVL equation around this loop. We've got a negative 6 volt source, we've got 6K times I, we've got 3K times I, and we've got negative 12, that equals 0. So that's 9K times I equals 18, divide by 9K, and so I equals 2 milliamps. So we can stick this up into here, and so we get 9 minus 12, which gives us a negative 3 volt open circuit voltage. Now the key thing with that is to recognize that as we start looking at our Thevenin equivalent, which is going to have that voltage source and that series resistor, we solve for a negative 3 volts, and the way that we'll express that in the circuit diagram is to just put the negative terminal of that voltage source on top and say, oh, that's a 3 volt source. The same difference. That's the open circuit voltage. Then we can go ahead and find what the Thevenin equivalent resistance actually is. So we'll come back to that one. We zero out the voltage source. We have the 6K resistor. If we can put both of these circuits on here. So there's the circuit that we're trying to quantify the behavior of. Here's the where we're finding the Thevenin equivalent resistance. So we got the 6 volt source is shorted, 6K resistor is here, 3K resistor is here, 12 volt source is shorted, and then we've got the 2K resistor sitting up here. And so again, this is a pretty, yeah.
6 volts? Like
It was
V
two
times
times
3,
two.
right?
It VLC.
The VOC should be...
The negative 3 volts up there should be negative 6.
Oh, yeah, I looked at the wrong part of my notes, and that's right. So you have 6 minus 12 gets you a negative 6. So let's update that over here. So this should be 6 volts. Thanks. This should be a pretty straightforward circuit to find an equivalent resistance for. The 1 and the 6 and the 3 are in parallel. That happens to work out to be 2 kiloohms that would be in series with the other 2 kiloohm resistor. So our Thevenin equivalent resistance is going to be 4 kiloohms total. So we can stick that into our analysis up here. That our Thevenin equals 4 kiloohms. We can hook up our load, and our load happened to also be 4 kiloohms. And as defined, we said that was the positive and negative terminals of that voltage V0. And so we have to be really careful about it as we figure out what's going on with this. And perhaps, maybe it makes more sense to you to say, well, let's put it this way, orient it this way, and say that we have negative 6 volts coming out of that source, and a 4K resistor here, and a 4K resistor here. They're equivalent expressions of the same thing. There's no difference between those two circuits. But maybe it makes more sense for you to look at it this way and realize that between these two 4K resistors, this voltage is going to be distributed evenly between the two of them. 4/8 would be the voltage division, so it's just going to divide in half, and that's a simple way of looking at that. Whenever you see the same amount of resistance, it divides equally between the two resistors. So you get that these are equals negative 3 volts. And the formal way of saying it is, well, we've got negative 6 volts coming out of the source, 4/8. Do you want to see one more independent source equivalent?
Sure.
Sure. One more? Okay. Try to find something that I have a snowball's chance of getting the right numbers for. So let's see. Let's try this one. This is number 523 out of the textbook. So there's the problem. The parameter that we're solving for is, we can call it V0, and it's the voltage across the 4K resistor at the top. And as much as anything, the reason for doing this particular problem is it's not always the case that our the parameter that we're solving for is at the far right-hand side of the circuit. So it's worth looking at this one to kind of get a clearer idea of what's going on with this circuit. But so we can pull out that load resistor, and the circuit that we're going to try to find the Thevenin equivalent for will look like this. So we need to find the open circuit voltage there. That should be equal to, if we write a KVL equation around there, let's make sure this works. So it should be that way. Given the way that the current flows around this loop, and the current should flow around that loop. So we should get, if we go around this way, we get VOC minus the voltage across the 2K resistor minus the voltage across the 6K resistor equals 0, or VOC equals the 2K resistor voltage plus the 6K resistor voltage. Now I am pretty certain that in this case, essentially these are going to be entirely separate circuits. That if we do a simple voltage division on the left-hand side, we can find out what the voltage across the 6K resistor is. And if we do, well, there's no place else for it to go, so we can figure out what the voltage across the 2K resistor is just by multiplying it by the current. This line is here, but it doesn't really indicate that these two circuits are connected in any way. So it's almost like there's two separate circuits. So the voltage across the 6K resistor should be the source voltage of 12 times 6 over 9. And I'm terrible. 9 times 12. It's just 8 volts. And then there should be 2 milliamps times 2 kiloohms of resistance. That's 2K. Equals 2 kiloohms resistance times 2 milliamps equals 4 volts. So the open circuit voltage should be 12 volts. So now we need to find the equivalent resistance, the Thevenin resistance for this circuit. So again, let's try to position the paper nicely. So we short out this voltage source, have a 3K resistor, 6K resistor, stuff over here. And this gets open circuited, that 2 milliamp current source. So we've got 2K resistor here, 6K, 3K. And we have to remember where we're looking at the circuit from. Where's the input terminals to this particular equivalent resistance? And looking at it from this point, and perhaps it even helps a little to ignore that, it's pretty clear that, again, we've got 3 and 6 in parallel with each other. Again, that works out to be 2 kiloohms of equivalent resistance. And then we've got another 2 kiloohms that would be in series with that. So the Thevenin resistance should equal 4 kiloohms again. So our open circuit voltage we solve for as being 12 volts. We found an equivalent Thevenin resistance of 4 kiloohms. And our load resistor was, again, 4 kiloohms. And we wanted to find the voltage across that. VO, V sub 0. And again, the voltage should divide evenly across those two, so V0 is 6 volts. And I'm pretty sure that I did that right, and that that should be the right answer. But I will check when I get back to my office to make sure that's right. So again, when we pulled that out, the hardest part here was solving for the open circuit voltage. And perhaps in this case, it might have been easier to do this as a Thevenin equivalent, or as a Norton equivalent maybe, and solve for the short circuit current instead of the open circuit voltage. And it's probably worth doing that real quickly, because I have a habit of not spending enough time on Norton equivalents. And it's important to be able to do that too. So let's look at this as a Norton equivalent problem. This is the same version of the circuit, except instead of solving for an open circuit voltage, we're going to solve for a short circuit current. And in this case, one of the things that's going to make this a somewhat more difficult problem is that it might be hard to do this in kind of one step, or we did it in kind of 2 steps by doing a voltage division and a simple current analysis, but Ohm's law kind of thing. But so we can do this as a mesh analysis. This is a pretty decent application for something like that. So here's I1, here's I2, here's I3. And 2 things that are worth kind of mentioning is that, well, whatever value that we get for I2 is going to be our short circuit current, and I3 equals 2 milliamps. So that's one thing that makes this a little easier. But so let's write our 2 mesh equations. First one, -12 plus 3k times I1 plus 6k times I1 minus I2 equals 0. We can simplify that one as 9k I1 minus 6k I2 equals 12. Second loop equation, we got 6k times I2 minus I1, and then 2k I3 minus, or I2 minus I3. We already know that I3 is 2 milliamps, so go ahead and stick that in there. Equals 0. So we end up with a negative 6k I1, positive 8k I2, and this will give us a negative 4 volts. Put that over on the other side, and that's 4. We get, so let's solve those simultaneously. 2 at 9,000, negative 6,000, 12, negative 6,000, 8,000, 4. And we get that I1 equals, it looks like it's 3.3 repeating milliamps, and I2 just equals 3 milliamps. Now, a good way to check that is, and to, I guess, to develop some amount of consistency between the work that we've done, is that our open circuit voltage should equal our short circuit current times our Thevenin resistance, right? And so if we've done this problem correctly, then the answers that we've gotten should be internally consistent. And one of the things that I will always do, especially when I develop problems, when I steal homework problems and put them on exams, and I have the solutions given to me, I don't worry about it so much. But when I write the problems, I will always double check the answer by doing the problem a different way. And so you can do this as a Norton analysis, and the answer should be consistent between the two of them. in the last version of the problem, when we solved for the open circuit voltage, we got 12 volts, and we found a Thevenin resistance of 4 kiloohms. And what should the short circuit current be if we did indeed do the the Thevenin analysis right? Well, the short circuit current should be 3 milliamps. Cool. It makes me feel good that I am apparently doing this problem right. So, the process of finding the Thevenin or the equivalent resistance is exactly the same as it was the last time. You open circuit that current source, you short circuit the voltage source, and you look in from the terminals of the load resistance that you had hooked up. It's the exact same thing. You don't have to duplicate that work if you don't want to. And so so this was our Thevenin equivalent. Our Norton equivalent. We solved for a short circuit current source of 3 milliamps and a Thevenin resistance of 4 kiloohms. And then our load was another 4 kiloohms. And so you could do a current divider, find that there was 1.5 milliamps flowing through each one of those branches of the circuit. If you have 1.5 milliamps flowing through a 4 kiloohm resistor, you get 6 volts again, both ways. So what we're doing makes sense. Let's try one more. And what I want is you guys to take a crack at it. I'll draw the circuit, put it up on the screen, give you a few minutes to look at it. If you have any questions, let me know, and we'll try to address those. So. Let's make it an easy one to start with. This is number 522 out of the textbook, so for your reference. So 522 has 2 kiloohm resistor over here. Six volt source here. That's a 4 kiloohm resistor. The 12 volt source. And our load that we've hooked up, that we want to know the voltage across, is a 2 kiloohm resistor. So that's the circuit that I want you to take a look at. See if you can. Let's start by just having you try to find the equivalent, the Thevenin equivalent. Don't worry so much about the actually solving for V0, but just try to come up with the open circuit voltage and the Thevenin resistance. And see, it's 10:13:30 right now. I'll peek back into you in about 3 minutes, about 10:16. All right, so let's take a look at what's going on here. And probably, again, the hardest thing in this is going to be making sure that you got numerically an answer that works for the open circuit voltage. So what we're going to do is we're going to break this circuit on just to the right of that 2K resistor, which is going to leave us with the circuit below here. We've got the 12 volt source and the 4K resistor, and the combination of the voltages across those two elements is going to give us the open circuit voltage. The important thing here, as you're figuring out how to combine these two voltages, is what is the polarity of those voltages going to be. And the weird one is going to be the 4K resistor, because as we're normally going around a loop, we're going to see, the current's going to be flowing around this way, based on our passive sign convention stuff and whatnot, so that it'll flow from the negative terminal to the positive terminal of the voltage source, and from the positive to negative of each one of the resistors. And so the polarity of the voltage on the 4K resistor is going to be, it's going to have the higher polarity at the bottom and not at the top. So when you if you were to write a KVL equation around this loop to make sure that you deal with the open circuit voltage appropriately, what you should end up with is something along these lines, that the open circuit voltage equals 12 minus the 4K resistance, or the voltage across that 4K resistor. If you want to think about it in a different way, and you wanted to say, well, let's just make this the positive voltage, say, well, it's just going to be the voltage, the sum of these two voltages across the 12 volt source and the 4K resistor. You could do that, but what you're going to find is that it's going to be a negative voltage, is defined that way, okay? So either way, what you should end up with is that there's 4 volts across the 4K resistor, and because of the polarity of the voltage, you have a total of 8 volts across as the open circuit voltage. People tend to get that, sort of, maybe? Yeah? Good. If you didn't get it and you don't understand how we got it, please let me know. The Thevenin resistance is pretty straightforward, because once you short out the two voltage sources, all that's left is this 2K and the 4K together. That parallel combination should be 4/3 of a kilo ohm. So our final Thevenin equivalent would be this 8 volt open circuit voltage, the 4/3 kilo ohm resistor up here, and then we could hook back up our 2K resistor if we wanted to find out the final voltage V0, and it would just be a voltage divider. 8 volts times 2 over, let's see, that's 6/3, 10/3 of a kilo ohm, whatever that wonderful fraction turns into numerically. So, you guys feeling comfortable enough with that? If you're not, again, please let me know. I'll be in my office, I think, most of the day today, so we can look at some more examples or something. But that's good old Thevenin equivalence with independent sources. Now, what you should have noticed, at least to some point, is that everything that we've done has been independent sources. And dependent sources, when it comes to Thevenin equivalence, are not fun at all. It's just, these get pretty nasty. And what we have to do is, if we have nothing but dependent sources, then one of the key things is that there will be no open circuit voltage or no short circuit current. The Thevenin equivalent for a circuit containing only dependent sources is solely the Thevenin resistance. But the only way to find out what that is to hook up a test source to the load terminals, and then find out, we have to solve for one of the other parameters. So if we hook up a test voltage source, then we solve for the current. If we hook up a current source, we solve for the voltage, and the ratio between the solved parameter and the test source value that you put in is going to give you your R Thevenin, and that R Thevenin is all that the equivalent actually is. The problem with this method, as much as anything, is there's no good rule of thumb or anything for which source you hook up. It's kind of whichever feels easier to you. Do you like solving for short circuit currents, or do you like solving for open circuit voltages? That's about the only thing that you have to work with. So let's see how this works out in practice, because it's, again, not particularly fun. So here is a circuit that contains only independent or only dependent sources. And in fact, this is the only dependent source that exists in this particular circuit. Next. And in this case, we've already detached the load, and we'll kind of come back and deal with that later. So what we will do in this particular one is we'll hook up a voltage source. So just go ahead and say here is a 1 volt voltage source. And what we need to solve for is the current I0 is what they've got it called, that is flowing through that branch. And so when we want to find out what the Thevenin resistance is, it's going to be 1 volt divided by whatever we solve for is the value of I0. So and I wish that I understood anything that I wrote on my notes. What is V1? Okay. So we need to solve this somehow, right? So perhaps what would be one of the easiest ways to do it is as some kind of mesh analysis, because we want to solve for a current anyways. So let's go ahead, call this one I1, call this one I2, call this one I3, call this one I4. And the important thing to remember is that I0 is a negative I4, whatever we get from our analysis. All right, so going around the top loop, we get, it's kind of unfortunate that we defined all of the currents going in particular directions, but anyways, we've got I1 times 1K times I1 up here. Then we've got 1K I1 minus I3, and then 2K I1 minus I2 equals 0. Simplify that one. We get 2K I1, 4K I1 minus 2K I2 minus 1K I3 equals 0. That's one that we'll need. On the second loop, we've got 1k times I2, we've got 2k I2 minus I1, and then we've got plus 2Vx equals 0. So now is as good a time as any to write the controlling equation for Vx. Vx is going to be, in terms of another circuit parameter that we have, it's actually going to be the voltage across the 1K resistor is I1 times 1K, but the polarity is to find the opposite direction that we wanted it to be in. So it would be Vx equals negative 1K times I1. So we can substitute that in. We've got a negative 2K I1 here. 2Vx would be another negative 2K I1. So we've got a total of negative 4K I1. And then we've got 3K times I2. And that equals 0. Then we got, in terms of the third loop, we've got another negative 2Vx, which, well, this time it's a negative 2Vx, so negative 2Vx will be positive 2K times I1. Then we've got 1K I3 minus I1, and 2K I3 minus I4 equals 0. And simplify that one, we've got positive 2K I1, negative 2K I1, so it'll give us just a total of 1K I1. We've got no I2s in there, so we'll stick in a 0K I2 just as a placeholder, just so we don't kind of forget it. We've got 1K and 2K, so that gives us positive 3K I3 and a negative 2K I4. And then our last equation, we get 2K I4 minus I3 plus 1 equals 0. And so that one simplifies out as 0K I1 plus 0K I2 minus 2K I3 plus 2K I4 equals negative 1. So there are the four equations that we'll solve simultaneously to get what is hopefully something vaguely correct when we're done. In equation number 2, so Vx,
Instead of negative 3K.
so we had in the I2s, yeah, thank you. 4 simultaneous equations. We've got 4,000, negative 2,000, negative 1,000, 0, 0, negative 4,000, 3,000, 0, 0, 0, 1,000, 0, 3,000, negative 2,000, 0, 0, 0, negative 2,000, positive 2,000, negative 1. And it seems like any of these answers could be correct because all of the currents should be extremely small and all are fractional. So the only problem is that they must all flow the opposite direction. I wish I had liked my notes better on this one. Because I don't like the answers that my calculator is giving me either. What what I'm getting is that I1 equals negative 0.43 milliamps. I2 is giving me negative 0.57 milliamps. I3 is also negative 0.57 milliamps. And I4 was negative 1.07 milliamps. So numerically, that actually works out to be the right answer. Oh, well, duh. Okay, it's obviously still too early. We defined I0 as being negative I4, and all that these negative signs mean in terms of the solution is that in reality all of the currents flow around the opposite direction, and I could have been more intelligent about defining the direction of my currents, and that would have pretty much taken care of it. So it works out that we did all of this analysis properly. I0 equals a negative I4, so I0 equals 1.07 milliamps. But that's only, again, half the problem. What we need to do is find out what the Thevenin resistance is, which is 1 volt over that 1.07 milliamps. 1 divided by 1.07 E3. Let's try that again. Which gives us 934. Yeah. 934 ohms. And I think if you have a calculator that gives you prettier numbers, I think the more exact form of the answer is actually 14 over 15 kilo ohms, for what it's worth. But mine is a slightly older calculator that gives me lots of decimal points instead of fancy numbers. Yeah.
I don't know, maybe this isn't like trivial or something, but like, I'm just kind of curious. So like, I4 negative whatever means that it's going actually counterclockwise through that loop.
Right.
And if I0 is negative of that, does that mean that I0 is actually flowing opposite of the way indicated by the arrow under it?
No, it's actually, let's see, if I4 is actually, now my brain is broken. So if I4, we've defined I4 as running around clockwise, and we solve for a negative number, which means that it's actually flowing around counterclockwise.
The only reason you define it negative is the way you define it.
Yeah.
So if you would
So,
switch.
no, I0 is flowing the direction as indicated by the arrow. It's just that I4 was poorly defined. And what would have made this problem work out a whole lot better is to actually have just defined all of the currents as flowing around the opposite direction. Because that would have made Vx wouldn't have had the negative sign. Most of the time when we run into this voltage source, it would have worked better. I4 would have coincided directly with the value for I0 and so on. Now I think you can, I think what I've actually got in my notes is a nodal analysis version of this problem. So that wouldn't be, it would be kind of maybe a little easier to do this as a nodal analysis problem, because in this case you've got the node at V2 is constrained to the Vx the 2 Vx voltage. At V3 it's constrained to the 1 volt, and so you didn't have to write 4 total equations to make it work. So it might have been a little easier as a nodal analysis problem, but we got it done as a mesh analysis problem. And the key thing was that we hooked up this 1 volt source, we solved for the current that was flowing through the source. The ratio of those two gives us our Thevenin resistance. And again, the Thevenin resistance is the sum total of the Thevenin equivalent for this particular circuit. Just one last thing to go through in terms of the solitary dependent sources, and I think that we should be able to get this done and maybe send you out here early here. Here's another one just to show you what it looks like to hook up a current source instead of a voltage source. So here's the circuit. Here are the terminals A and B that we're hooking stuff up to in the first place. And we're going to hook up a 1 milliamp test source. Two kilo ohm resistor here, 3 kilo ohm resistor here, 1 kilo ohm resistor here, 2 kilo ohm here. This is a voltage source that is 2000 times Ix, and the current Ix is what's flowing through the 1 kilo ohm resistor. So I think the easiest way to do this one will be a nodal analysis, because what we need to solve for in the first place is we need to know what the voltage is across this 1 milliamp source. That's what we need to solve for. And so essentially once we get the value for V2, we have what we need to do this one. So we have V1 minus the source here, 2000 Ix over 2K plus V1 over 1K plus C1 minus V2 over 3K equals 0. And then at the second node, we've got V2 minus V1 over 3K. That's V2 over 2K plus, well, that current's actually coming in. So let's go ahead and, it would actually be a negative current 1 milliamp coming in, so let's just stick it over on the other side, make our life easier. Now we need the controlling equation for Ix. Ix is just the voltage, is the current that's running through the 1 kilo ohm resistor. The current running through that 1K resistor is the voltage across the 1K resistor divided by the resistance. The voltage across that resistor as given in the problem is going to be this node voltage V1. So Ix equals V1 divided by 1 kilo ohm. So we can substitute that back in up here. And as much as anything, well, let's start separating terms out too. So we got V1 over 2K minus 2000 Ix. 2000 Ix would be 2V1 over 1K. That's not right. We got the negative 2000 times Ix would be 2000 or 2V1, and the 1K goes away. And this should be a 2K. Today's not my day. The math works out on that one, right? All right. So we had the 2000 Ix. We multiply 2000 times this. We get 2V1. So that's the 1K goes away, and we get 2V1 over 2K. And that's what we're left with there. Plus V1 over 1K plus V1 over 3K minus V2 over 3K equals 0. And then this one is just, we can just say negative 1 over 3K V1 plus 1 over 3K plus 1 over 2K times V2 equals 1 milliamp. for purposes of time, so those are our two equations. As far as I know, I didn't mess anything up mathematically there. If we solve those two equations simultaneously, we get that V1 equals 0.571 volts. I should just do this, but V2 should equal 1.43 volts, which should be more or less equivalent to 10 over 7 volts. But let's plug this in just to make sure. I hate having people come back to me and say, oh, this math wasn't right. So in the first one, our terms on V1, we've got 1 over 2,000 plus minus 2 over 2,000 plus 1 over 1,000 plus 1 over 3,000. Okay. And then we've got negative 1 over 3,000. That should equal 0. On the next one, we got negative 1 over 3,000. We got 1 over 3,000 plus 1 over 2,000. And that equals 1 to the negative third. Okay, yeah, those numbers, these numbers do work out if you solve for those two equations. At least I'm getting the same numbers again. So anyway, so that's what our two node voltages should be. And then once we know what this node voltage V2 is, to find our Thevenin, we say, well, we need to know what that voltage is. That's V2, so it's the 1.43 or 10/7 over the 1 milliamp of current. And all that really does is kicks this up to 1.43 kilo ohms. So the point of both of those is to show you that you just hook up these test sources, you solve for the opposite parameters. So if you hook up a voltage source, you solve for the current. If you hook up a current source, you solve for the voltage. The ratio between those two things is going to give you the Thevenin resistance, and that's the only parameter that actually shows up in your as your Thevenin equivalent. So the likelihood of seeing more than like 2 of these dependent source only problems for the rest of my class is pretty low, because there are more interesting problems to do, but it's the kind of thing that you might throw like one problem at you on the homework and maybe one problem on the final or something like that. It will be my third priority today. So first priority is finishing the exam, second priority is grading the quizzes, third priority will be posting some homework for this particular thing. The reason that I went into so much detail on the Thevenin equivalents with the independent sources is that's the only part that's going to show up on the exam. So I wanted you to be comfortable with that, have lots of examples to work with, and perhaps I'll even put up a couple more solved problems on the website for you so you can feel comfortable with it. So let's see, plan for tomorrow then will be to continue with Thevenin equivalent stuff. The next thing to look at is what happens when we have a mixture of independent and dependent sources. And in that case, it's just not fun because you have to solve for the open circuit voltage and the short circuit current, as if this wasn't hard enough already. If you have questions on the Thevenin analysis stuff or anything else, let me know. What we will certainly do is for the last half an hour at least, I will give you an idea of the kinds of things that I expect, well, the kinds of things that are on the exam, the things that you should solve for and be able to deal with going into the exam, give you an idea of what to expect on it in general. And perhaps we can even, depending on how far we get on the dependent source equivalents or mixed source equivalents, just do some problem solving or questions. So that'll be the plan for tomorrow. Have a good one. I will have quizzes for you to hand back graded There will be no quiz tomorrow, just the exam. So we'll see you tomorrow.